Now let us have an example for inverse of functions. Let's say we have a given y is equal to 0.5x squared plus 2. What we want to get is to make a table of values for f negative 2, f negative 1, f of 0, f of 1, and f of 2. From the numbers in the table, explain why you cannot find a unique value of x if x is equal to 2.5. How does this result tell you that function f is not invertible? So as you can see here, we have a premise here that somewhere in those values from negative 2 to 2, there is a certain value wherein f of x is equal to 5. Let us investigate further. So I prepared here the table. It's already prepared. Okay, so this is our tabular representation for the domains from negative 2 to 2 for the given function y is equal to 0.5x squared plus 2. Now let us investigate this function. If our x is equal to negative 2, so if our x is equal to negative 2, then our y is just equal to 0.5 times negative 2 squared plus 2. And that gives us a value of 0.5 times 4 plus 2, which gives us a value which is equivalent to 2 plus 2, and that's equal to 4. As you can see, that confirms with our f of x on the table on the right. Same is true when your x is equal to negative 1. Now let's investigate our negative 1. So if x is equal to negative 1, then our y, or our f of x, which is just our y, is equal to 0.5 times negative 1 squared plus 2, which is equal to 0.5 times 1, because negative 1 raised to a square, or anything negative raised to an even exponent, becomes positive. So that will give you 0.5 plus 2, so that's 2.5. Now you try doing this until x is equal to 2. So do it until x is equal to 2. And you will see that the values that I get here on the right and the values that you will get on wherever you are working on will have the same x and y values. So we are particularly investigating this portion, this f of x values here. And as you notice, we have highlighted, I have highlighted f of x of certain x values here, which are we have this one, the first one, negative 1, wherein the f of negative 1 is 2.5, and we also have our 1, wherein f of 1 is equal to 2.5. Let me erase this part here. Okay, so now we have a cleaner thing, and I'm going to highlight those that have duplicated values. So we have this one, and we have this one. So from the numbers in the table, explain why you cannot find a unique value of x if x, or if f of x is equal to 2.5. Therefore, we have proven that our f of x is equal to 2.5. There are two x values. There are two x values, negative 1 and 1, which have the same f of x value or y value, which is 2.5. So this result tells us that this function, okay, this function here is c, okay, is not invertible, because as we have already discussed before, one of our requirements for a function to be invertible is for it to become one-on-one or one-to-one. When a function is not one-to-one, such as in this case, you can see there, we could see something like -1, 2.5. So -1, 2.5, and 1, 2.5. Or in the case of graphing that, we have 1 and -1. We have -1 here, we have 1 here, and we have 1, 2, 3. So we have 2.5 here. So we have a point here for, let me give that another color. So we have here two values for x with the same y value. And if we are going to connect these two lines here, or these 2 points here, then we could see that if this is like, if we draw a curve here, for example, this is the function, and I'm pretty sure that the function looks something like this because it's a quadratic function. So if you can see, this is not one-to-one. This is many to one, which fails the requirement for and when a certain given function fails to fulfill the requirement of invertibility, then we couldn't get an inverse for this function. It can't have. So one of the requirements is one-to-one. What is another one? It should be strictly increasing or decreasing, meaning it could be something like a linear function, wherein from the graph it is, this is our y-axis, this is our x-axis, it is increasing strictly or increasing or decreasing strictly. So those are the two requirements for a function to be invertible. And in this case, this is a quadratic function, and we could see from the given tabular representations here that it fails to have a unique value of y for a certain value of x, because for two values of x, we have only one value for y, which is 2.5. Okay? Therefore, our function f of x, okay, our function f of x does not have, f of x is not invertible. As you can see in the in here, okay, function f is not invertible because we have two values of y. You have two values of y for the same x value in the variables when the variables are interchanged. So when you interchange your x and y, you will have the same x value, okay, for a certain for a certain y value. Do you get it? It's like this. When you flip this on the same screen, for example, in this case, for in the same screen, it says something like this. So it goes like that, okay, and this is 2.5, so it has the same x values, okay, for two y values. Let's say this is -1 and this is, this is +1, this is -1 for the y values, and as you notice, if we flip this, if we get the mirror of this within the parameter or across the borders of our y is equal to x line, this is our y is equal to x line. Y is equal to x. This is our mirror. That's our boundary of judging. And as you can see, if you flip this portion here, this graph here of the quadratic function, then it would look like that. And if we're going to perform a test, which is a vertical line test, they call it a vertical line test. As you can see, we have the same x value for two y values, and therefore it is not. This is not a function. Okay, it's a relation. The inverse is a relation. That is why we cannot have an inverse for our original function f, and therefore it is not invertible. And what is the essence of this? We cannot write f negative 1 of x for f of x. And that's it. So given the same problem, y is equal to 0.5x squared plus 2, let B plot the 5 points in part A on a graph paper. So if you have a paper there, you can get your paper and then try to graph this values for x and y, which is similar to this. Okay. So the table on the right that you see is our original tabular values for the domain of f of negative 2 to 2 as is presented on the first slide. We have f negative 1, negative 2, rather, negative 1, 0, 1, and 2. This marks our domain. So our domain basically is from x, which is in between negative 2 and 2, and including, or it's from negative 2 to 2. So that's our domain. So we get these y values here. If x negative 2, y is equal to 4, and so on and so forth. So what we're going to do here, is to graph these pairs of points into the coordinate axis that you can see. We have our y-axis here, and we have our x-axis here. Therefore, let's graph the values. If our x is equal to negative 2, then we have 4. We need a grid line. Okay, let's fix the position of our graph so that it tallies with our grids. So we have negative 2 and 4. So we have negative 2 and 4. It's here. Let's make it bigger. Let's make the points bigger. Okay, so it's here. Okay, we have negative 1 and 2.5. Negative 1 and 2.5, so it's somewhere here. Okay, we have 0 and 2. We have a y-intercept here. And I'm assuming this is the vertex. We have 1 and 2.5. And we have 2 and 4. So I am correct that it is the vertex because it is the lowest point of the curve. If you are going to connect it, we will get a curve, and that's the lowest point of the curve that we will get. Therefore, it is the vertex of that parabola. That's a parabolic equation because it is a quadratic function. Okay? So we're going to connect the curves now. We're connecting them. Oops.